Welcome at the course Laser-Matter Interaction. This is the very first lecture of the course. The lecture is dedicated to the main approximations. Well, as we all know, light is electromagnetic wave. We also know that condensed matter, molecules, atoms, they all consist of quantum mechanical particles. Electromagnetic waves can be modeled using Maxwell equations. Quantum mechanical particles can be modeled using Schrödinger equation. So you can ask me, why do we need this course at all? Well, of course, if you take a realistic medium, it could be a condensed matter system, metal, dielectric, a semiconductor, superconductor, or even a molecule. And if you try to write a complete model that will take into account all the details of these objects, the model would be too complicated to be solved analytically. So in this case, of course, we use computers. So in these days, the computers are so powerful that they can calculate everything. However, how will you evaluate the validity of the model? How will you evaluate and verify correctness of the results that you obtain? That's an interesting question. Or a different example. Imagine you perform an experiment and you have to decide, looking at the experimental data, if it is in interesting physics or not. Or you have to decide if this is a subject that deserves an additional checks, an additional experiments to figure out whether what you measure is a result of artifact or it is a real effect. For this, for all these examples, you need to have a simple, intuitive model of the object that you study. And having a model means we have to simplify the object that we study using approximations. And here I would like to quote famous physicist Lev Landau, and one of the quotes which is assigned to him is, most important part of doing physics is the knowledge of approximation. So if you want to build an intuitive and simple model, you have to simplify the problem. You have to do approximations and neglect things which are not important, and then leave and stay with the things which define the main physical observations and the effect that you study. Let's define approximations, which allows us to build a very simple model of light-matter interaction. And the simplest possible model of light-matter interaction would be the goal of the very first lecture. Well, as we all know, light is electromagnetic wave. So then it means that we will treat light as a classical wave. We will not treat light as a quantum mechanical object. So light in our course will not be a flow of photons. It will be a wave. You may ask me whether it is a reasonable approximation. Well, in all the experiments I will be talking about, we will have high intensities of light sources, and as we all know, the most advanced source of light these days is a laser. Laser is a source of light which produces radiation of very high intensity. And if you have high intensity, it means we have plenty of photons, and we have plenty of photons, it means that we have enough particles to satisfy the rule of a large number, and it means these quantum mechanical particles, photons, will behave altogether, will behave in accordance with the statistics predicted by wave. So basically we have so many photons in our light sources that having approximation of having a classical approximation for light is a reliable approximation. So we will assume that light is a classical wave, classical electromagnetic wave. And since light is electromagnetic wave, then we can write series of Maxwell equations. These are 4 Maxwell equations where E is electric field of light, H is magnetic field of light, B is magnetic induction, D is a vector of electrical displacement, and of course do not forget that not all the quantities are mutually independent here. P is the polarization, epsilon 0, and as I system of units is fundamental constant, then we have vector of magnetic induction, mu 0, also fundamental constant, m is the magnetization, and ρ is a charge density. These are 4 Maxwell equations we start with, and here, looking at all these Maxwell equations, we may already make steps towards simplification. The very first approximations, the most about light-matter interaction that I would like to make is the approximation which is called electric dipole approximation. What does it mean? Well, light is an electromagnetic wave. It has electric component and magnetic component. Electric component will interact with charged particles. Magnetic component will interact with magnetic moments. Imagine that you are at the beginning of 20th century, even at the end of 19th century, when people try to develop the model of light-matter interaction using, in particular, Maxwell equations. And at that time, of course, there was no knowledge about the fact that electron has spin. There was no knowledge of the fact that, that the particles in condensed matter have magnetic moments. But there was a good understanding of the fact that condensed matter systems contain charged particles. And even at the beginning of 19th century, it was known that the lightest charged particle with the smallest mass is an electron. So then, looking at the interaction of electric component of light with some parts of matter, magnetic component of light with other parts of matter, then of course we could say at that time that interaction of electric component of light with charged particles will dominate the interaction. And this is basically the main sense of the electric dipole approximation. So we assume that if you talk about energy of light-matter interaction, it would be energy of interaction of electric field of light with electric dipole. An electric dipole is defined in classical physics as a vector which is equal to the charge times distance, and it is defined for a system of positive and positively charged and negatively charged particle. The charges are the absolute values of the charges are equal. But on different particles, they have different sign. This is how it is defined, how the dipole moment defined in classical physics. In quantum mechanics, the definition is different. So then, energy of light-matter interaction would be defined by this scalar product. And, well, do not forget, of course, that if you want to define energy of light-matter interaction over the whole sample, then you have to take sum over all electric dipoles that light will interact with in a medium. So this is called electric dipole approximation. And what does it allow us to neglect? This basically allows us to state that magnetization in the medium is equal to 0. We do not care about other interactions in the medium, and in particular about the interaction of magnetic field of light with magnetization. So if we do not care about this interaction, we assume from the very beginning that the magnetization is 0. So once again, optical response of medium is determined by interaction of electrons with the electric component of electromagnetic wave. And this is the main statement behind electric dipole approximation. Well, let's now take this approximation and look what do we achieve with this approximation if we have Maxwell equations. M is equal to 0. Just for simplicity, I will assume that current density is equal to 0 and charge density is equal to 0. It will make derivations shorter. And then what I will do now, I will take curl from both parts of this equation the next step is to work with this part of the equation, with the right part of the equation. And what we assume here is that this vector product is practically equal to this expression. So basically what we do here, we change the order of differentiation with respect to time or with respect to coordinates. If here we first differentiated with respect to time and then with respect to coordinates, here we differentiate first with respect to the coordinates and then with respect to time. We can do this only if if magnetic induction varies slowly. And it means that if we take this derivative, it is neither derivative of magnetic induction with respect to time, no derivative of magnetic induction with respect to coordinates, diverges and goes to infinity. So it means that B varies slowly. In principle, if you talk about realistic optical signals and the experiments that we are going to describe, then all these cases B varies slow enough to apply this approximation. Then we apply here one of the Maxwell equations. Remember that magnetization is equal to 0. And what we observe, if you look at this derivation, is that here we can write mu 0, then second derivative with respect to the vector of electrical displacement. Well, of course, vector of electric displacement is equal to electric field times fundamental constant plus polarization. And let's first look at the case of vacuum. So that electromagnetic wave propagates in vacuum. Just for simplicity, we assume that polarization is equal to 0. It will not be the case in the rest of the course, but just to look first at the simple form of this equation, we assume that we're talking about vacuum. And then we will see how much things change if P is not 0. How many things will be changed if P is not 0. Then if P is 0, here it will be minus epsilon second derivative T then from textbooks on mathematics you can find that if you have a vector product of 3 vectors, then it can be expressed in terms of the following combination of scalar products. And an application of this expression to this vector product, we obtain this expression. And since we assumed that charge density is equal to 0, this part of the expression will be 0. And what we get here is an expression like this. It is an expression for electromagnetic wave in vacuum. Now, let's take a simple case. Let's take a case of an electromagnetic wave that propagates just in one direction. So this will be electromagnetic wave that propagates just in the direction of x-axis. So be 1 over 2. This is amplitude. Then we have minus I omega t plus k, where k is the wave vector, x is the coordinate. And then we have complex conjugated number next to it. So if you put this expression to here, you will see that this expression will simply give me wave vector in square times vector of electric field. And this derivative will give me minus omega, the frequency of the wave, and then again vector of electric field. Substituting these two expressions into this equation, we obtain that wave vector in square is equal to mu 0 epsilon 0 omega square, and since wave vector is 2 pi divided by lambda, lambda is a wavelength, and it means it is equal to omega divided by c, where c is the speed of light at the vacuum. From here you can find that the speed of light in vacuum is equal to epsilon 0 mu 0. This is just confirmation of the results that you most likely know already, that if you want to calculate speed of light in vacuum, you just take a square root of epsilon 0 mu 0 and take inverse of it. Well, this, as I said, it's a simple case to show what we have when light propagates in a vacuum, but now I would like to understand light-matter interaction of light with something that contains charged particles. In this case, electric field of light will induce polarization. Polarization will not be zero. If polarization is not zero, then here I have to work not with electric field and the strength of the electric field, but with vector of electric displacement. And now you can ask me which polarization I should put here. What is a polarization? Obviously, polarization will depend on electric field of light. This is the polarization which is induced in the medium by the electric field of light. And if you ask me about the form of this function that defines the dependence of the polarization on the electric field of light, the answer will be it is the goal of the whole course. Actually, during this course, we will try to understand this dependence. Well, the first step towards the simplest model of light-matter interaction is to assume the simplest possible dependence here. And the simplest possible dependence that we can assume here is a linear dependence. If you state that polarization induced in the medium by the electric field of light is a linear function of the electric field of light, it is called linear optical approximation. So this is approximation of linear optics. Of course, if the electric field becomes stronger and stronger, then the linear dependence will not be valid anymore, and you will have to take into account higher orders. So let's put not a vector here, but scalar, so it will be easier to write down the expansion in Taylor series. Here it will be some phenomenological coefficients which will define a response of the medium, response of the polarization to the electric field of light of the first order, second order, and third order with respect to the electric field of light. In principle, if you talk about very high intensities, it means electric field of light is high, is very strong. then it means that we have to take into account higher orders in this expansion. But if the electric field of light is small, we will be satisfied with linear approximation, and this is called linear optical approximation. What is strong and what is weak? Well, if you want to understand this, you have to compare the electric field of light with interatomic forces. And the force, the electric field that acts between two atoms and crystal lattice is equal to 2 volt per angstrom, approximately. So say upon approaching this quantity, more and more nonlinear corrections should be taken into account to linear optical should be taken into account to describe light-matter interaction. But if you work with very low intensities, when electric field is much smaller than this quantity, and the intensity is weaker and weaker, it is more and more reliable to work in linear optical approximation. What is what would be the reference here? As a matter of fact, linear optical phenomena were discovered only with the use of lasers, so rather intense sources of light. And if you use just a normal source, regular source of light, like a lamp, or if you even use a sunlight, then you will be very safe if you just use linear optical approximation. Well, here we have linear optical approximation. Another approximation that simplifies our life enormously is approximation of isotropic medium. Why? Because if here electric field of light is the vector, polarization induced by this electric field in a medium is the vector, the quantity that relates to vectors is a matrix. And well, in the most general case, if you want to understand polarization induced in a medium by the electric field of light, you have to know this matrix. But you can also find media where, for whatever direction of the electric field, polarization induced in the medium is always parallel to this electric field. And in this case, this quantity that relates electric field of light and the polarization is a scalar. If you can write this expression, it means we work in the approximation of isotropic medium. So what we have here, we have linear optical approximation, approximation of isotropic medium, and it means that polarization of light can be calculated just taking linear relation with one unknown coefficient, one unknown scalar, chi. And here, I just need to make one more step to make model more or less completed. If before I was talking about energy of light-matter interaction in terms of scalar product of electric field of light and dipole moments with which this electric field interacts. Now, I would like to pay attention to the fact that the distance between dipole moments in the medium is very small compared to the wavelengths of light. If you look at the realistic condensed matter systems, and if you look at the distance between atoms, it is of the order of 1 nanometer. And this is much smaller than the wavelengths of light. If interatomic distance is, well, imagine it's 1 nanometer, the wavelengths of light is 500 nanometers. Obviously, wavelength is much larger than interatomic distance, and it means that on the scale of wavelength, we will have so many dipole moments that it's simply safe to take an average over all these dipole moments over the volume covered by one wavelength. And if you calculate the average of all dipole moments over the volume, the quantity you will get is the polarization. So this is the final link between electric dipole approximation and this expression. So now I have already very clear picture. What's going on here? Electric field of light interacts with electric dipoles, induces polarization in the medium. This polarization enters wave equation, this equation, which we derived based on Maxwell equations, and define electric field emitted by the medium afterwards. So once again, if we know polarization, we can calculate electric field emitted by the medium with this polarization. And the polarization is induced by the electric field of light. And this chain can describe as light-matter interaction. The goal of the course is to understand this link. But this link can be understood with the help of two approximations. One is linear optical approximation, and the second approximation of isotropic medium. Then, if you assume this approximation, and you remember this definition for the vector of electrical displacement, you can see here that D would be also linear function of electric field. And coefficient which defines this proportionality is just chi plus 1. And chi is a proportionality coefficient between electric field and the polarization. So, to summarize, what we did, we accepted several approximations. First, electric dipole approximation, which stated that light-matter interaction is given by the scalar product of electric field of light and dipole moment induced by this electric field in the medium. Second, approximation that instead of dipole moment, we're going to work with polarization. In this case, it is we basically substitute the energy of light-matter interaction with more practical expression, which would be given by the product of electric field of light and the polarization. This approximation, the second approximation, is called approximation of continuous medium. Then the third approximation, linear optical approximation, assuming that, that helps us to assume that the relation between the electric field of light and the polarization is linear. Then we assume approximation of isotropic medium. It means that this matrix that relates vector of electric field and the polarization becomes a scalar. And it means that vector of electric displacement and the polarization are always parallel with respect to the electric field of light. If you use these approximations, and if you put them eventually into this expression, what you will get is expression for speed of light in a medium with epsilon here in the denominator. And as we all know, if this is speed of light in a medium, this is speed of light in a vacuum, by definition, speed of light in a medium is less than speed of light in a vacuum by n, by factor of n, where n is the refraction coefficient, and the refraction coefficient will be given just by the square root of epsilon. This proportionality coefficient between vector of electric displacement and the electric field. Well, as you can see, now we arrive to a very simple model of light-matter interaction, which is defined with just one coefficient, epsilon. What can we say about epsilon? In order to get a better feeling of this quantity, I propose to accept one more approximation that sounds very weird. It is approximation of no dissipations. What does it mean, dissipations? Dissipations means irreversible energy transfer from light to matter. If you assume that there are no irreversible energy transfer from light to matter, then it means that there are no dissipations in the process. What does it mean? No irreversible transfer. How can we express this mathematically? If we talk about electromagnetic wave and define the Poynting vector for this wave, if we assume no irreversible energy transfer from light to matter, it means that divergence of the Poynting vector must be equal to 0. So if you look in the process of light-matter interaction, it means that in the process of light-matter interaction, energy that entered specific points of the medium will leave this point of the medium and will not deposit any energy into the medium. It may deposit it for a short time, but on a longer time scale, all energy should be released from these points and emitted from this point. So basically, light will not increase temperature of the medium. If you look at the divergence of this vector product, again using textbooks and mathematics, you can express this differently. And if you look at this part, and in this part, you recognize the parts of Maxwell equations. So you can see now that these parts will depend on mu, and these parts will depend on epsilon. So let's see what it means that divergence is 0. For simplicity, I will work with sinusoidal waves. And again, for simplicity, I will assume that wave depends only on time, because here only dependence on time is important because it is derivative with respect to time, which is taken here. And that means that here I take and the same I will assume for vector of electrical displacement. It will be also wave. Obviously, we should keep in mind the following relations between amplitudes of electrical displacement and the amplitude of the electric field. And if you take this derivative and calculate the product, you practically have to find the result of multiplication of these rather long but simple expressions between parentheses. And here what you will get is EM epsilon exponential function e2 omega t plus EM complex conjugated epsilon minus I2 omega t, and the most interesting, cross terms, cross multiplications. This term and this multiplication, and it is first of all for this one. Yes, it is EM complex conjugated star exponential 0 plus EM E epsilon again 0. You can see that this term and this term, they oscillate in time. They oscillate in time at the frequency twice the frequency of light. And if you talk about divergence of this quantity, there is energy transfer from light to matter in one period of this oscillation. But there is also opposite process, transfer of energy from matter to light in the other half period of this oscillation. So it means that these terms do not contribute to the irreversible part of this divergence. Basically, if you want to understand irreversible energy transfer between light and matter, you have to look at the divergence, but also keep in mind that we are talking about waves, and then if the energy is transferred from wave to light at one half period, then in the another half period we may encounter the opposite process. The energy will be transferred from matter to light, and then it means that to be on the safe side you have to take an integral over time here, and so that you make sure the average out over many periods. Then it means that these two terms do not contribute to irreversible energy transfer from light to matter, and we stay only with these two terms in our discussion. And if you assume that divergence of Poynting vector is equal to 0, basically it would mean that we must assume that epsilon must be equal to its complex conjugate. So it means that epsilon is a real number. Well, the very same logic will bring you to the conclusion that mu is also a real number. You will have to repeat the very same steps, but not with electric field, but with magnetization, and not with a vector of electrical displacement, but with vector of electromagnetic induction. And you will get the very similar answer here, that mu should be a real number. Well, let's try to summarize what we have achieved so far. We have learned that if we take 4 approximations on which the approximation of electric dipole, approximation of continuous medium, approximation of linear optics, and approximation of isotropic medium, the light-matter interaction can be described just with one number, with one quantity. It is quantity epsilon. It's a scalar. And if you assume that there are no dissipations in the process of light-matter interaction, this basically means this epsilon must be a real number. And these 5 approximations give us the simplest model of light-matter interaction. Well, at the very beginning of the lecture, I also assumed that we take approximation that light is a classical electromagnetic wave, but it's more related to light than to light-matter interaction. That's why in the rest of the course, we will focus on these 5 approximations. Once again, electric dipole approximation, approximation of continuous medium, linear optical approximation, approximation of isotropic medium, and approximation of no dissipations. And the goal of the course will be to show you what we actually overlook accepting each of these approximations. What physics do we miss if you assume that there are no dissipations in the medium? What are the physical phenomena that we overlook that we assume, when we assume that the medium is isotropic? What does it mean if we talk about nonlinear optics? And of course, approximation of continuous medium is also very important. And if you are wondering about the transition between, in principle, very simple, I would even say classical physics to quantum physics, then the transition to quantum physics will occur at this step. And one approximation we will not have time to talk about will be approximation of electric dipole. So basically everywhere in the course I will assume that electric dipole approximation is always valid. As a matter of fact, interaction of light, interaction of electric field of light with electrons is the strongest interaction in the process of interaction of light and matter, if you talk about visible spectral range. That's why this approximation would be central in the whole course, and I will always assume this is true. Well, these 6 approximations, as I said, it's also 5 approximations, as I said, is also take-home message for the lecture today. And next lecture, we will start thinking about consequences of this approximation of no dissipations for physics of light-matter interaction. Thank you very much.